Hello everyone, welcome to the second part of this intro to trigonometry. So we're going to start with where we left off at the end of the last video, and then we're going to go on to do a couple of examples to see how we can use this stuff. So trigonometry, we started with saying if I have a right-angled triangle, and then I have another angle in this triangle, let's call that angle theta. I can label each of the sides of this triangle and I can give it a name which tells me where it stands in relation to that angle theta. So this side length here is the side that is opposite my angle, so I call it the opposite side, or O for short. This side here is the side that is next to or adjacent to my angle theta, so I'm going to call it the adjacent side, or A for short. And then this side here, the side that's opposite the right angle, is always the hypotenuse, or H for short. And we discussed in the last video how if I have any other right-angled triangle with that same angle theta, then it must be a similar triangle to this one. And if it's a similar triangle, then all similar triangles have the same ratios of the side lengths will have the same ratios to each other. So the ratio of the opposite side to the hypotenuse, for example, will be the same for any right-angled triangle if it's got that same angle theta, because that's a property of it being a similar triangle. Because of that, we can develop machines. That's kind of what we call them. It's just a way of thinking about them. And we want 3 machines. And the idea of each of these machines is we want to develop some sort of thing where I can input an angle, theta, and out will pop the ratio, each of these ratios. So first I want a machine where I can put into the machine an angle theta, and out will pop a number which represents the ratio of the opposite side to the hypotenuse. I want another machine where I can put in an angle theta, and out will pop a number which is the ratio of the adjacent side to the hypotenuse. And I want one last machine where I put in an angle theta, and out will pop a number which is the ratio of the opposite side to the adjacent side. And we gave each of these machines a name. This was the sine machine, this was the cosine machine, and this was the tangent machine. And then we said we can take this one step further and we can also flip it around. And if we turn it around, then it allows us to put in a ratio and get out an angle. But instead of flipping it around, I'm going to draw it again, and I want you to imagine that what's happening is that the machine is being flipped. But if the machine's being flipped so that I can put in a ratio and get out an angle, then I need to flip the machine itself. So sine is now flipped upside down, and it's now, instead of being sine, it's now the upside down, or the inverse of sine, which we write as sine to the -1, like that. That means the inverse of sine. Similarly, the inverse of cosine means that I can put in a ratio. I can put in a number, which is the ratio of the adjacent side to the hypotenuse, and out will pop an angle. And I can have a machine which is the upside down tan, or the inverse of tan, where I can put in a number, which is the ratio of the opposite to the adjacent side, and out will pop the angle theta. Okay, the reason why I'm talking about these sine, cos, tan things as machines is because I don't want you to ever get confused and start using them as numbers. This angle that goes in is a number, and the ratio that pops out the other side is a number, but the sine or the cosine or the tangent itself is not a number. It's a function, or a machine, if that's kind of an easier way of thinking about it. And so when we come to starting when we start to manipulate equations, we can't think of sine as a number that we can, move over to the other side of an equation. We can only think of sine of theta, which means that we've put theta through the sine machine to get another number. Then it's a number and we can move it over. That might not have been clear, but hopefully it will become clear as soon as we start doing a couple of examples, which we will start doing right now. So here is the first couple of examples that we're going to do. Question 1 here has a right-angled triangle where with an angle of 40 degrees, a hypotenuse of 8 centimeters, and then an adjacent side length of x. So just to make it really clear, I'm going to start by labeling each of my side lengths in relation to my angle. So that's the hypotenuse, this is the opposite side length, and this is the adjacent. And once I do that, it should become pretty obvious that I need the adjacent over the hypotenuse ratio, because those are the two side lengths that I'm interested in here. So I'm going to jump back to my little diagram here. I'm also going to make use of this abbreviation that we spoke about, SOHCAHTOA. And if I need the adjacent over the hypotenuse, then I want to use the adjacent over the hypotenuse, which is the cosine ratio. So I'm going to start by writing that the cosine of theta, so that's how I write it. That means that I'm taking theta, the angle, and I'm putting it into the cosine machine, equals the adjacent over the hypotenuse. Then I'm going to fit in whatever numbers I have. So I've got the cosine of 40 degrees, and I can put the thing that I'm putting into the cosine machine in brackets, just to make it really obvious. So I've got the cos of 40 degrees equals the adjacent, which is x, over the hypotenuse, which is 8. Now remember, the cosine itself is not a number, but the cosine of 40, that's a number, because when I put 40 into the machine, a number pops out. So this whole thing together is a number. So I can rearrange this equation the way I would any other linear equation, where I've got an x I want to isolate. I'm going to multiply both sides by 8 to move the 8 over to the other side. So those 8's going to cancel, and I'm going to get that x equals 8 times the cosine of 40. And when I put that into my calculator, 8 times cos 40, I get 6.13. Okay, question 2. I've got my angle here, 70 degrees. I'm going to label my side lengths again. Notice this time my opposite and my adjacent side lengths have kind of swapped places to what they were last time because my angle's in a different place. So the side lengths are always labelled in relation to the angle, not in relation to, the position of the triangle or anything. Here, my two side lengths I'm interested in are the opposite and the hypotenuse. So I'm going to use the fact that sine theta equals the opposite over the hypotenuse. Let's put in the numbers that I have. Sine of 70 degrees equals 15 over x. And here, to rearrange this, it's a little bit more difficult because I've got x on the bottom of a fraction. But that shouldn't be too hard for us because we've discussed how to do that before. The way I'm going to do this is I'm going to start by multiplying both sides of the equation by x. That's going to move x over to this side and get it off the bottom of the fraction. So I get that x sine 70 equals 15. Remembering that sine of 70 is just a number, that gives me that x equals 15 divided by the sine of 70. And when I put that into my calculator, 15 divided by sine 70, I get 15.96. Okay. Let's do 2 more examples. Question 3 here is now giving me side lengths. So if this is my angle theta, then this is the hypotenuse, adjacent, and opposite. It's giving me 2 side lengths, and I need to find the angle. The 2 side lengths it's giving me are the opposite and the adjacent, so I'm going to use the fact that tan of theta equals opposite over adjacent. Let's put in whatever numbers I have. Tan theta equals 6 over 20. And now, because I have both numbers on this side, 6 divided by 20, well, that's just a number. So I have an input that I can put into my upside down machine. I have opposite over adjacent that I can put into this machine to get a angle out the other side. So that means I need to flip my tan machine upside down, and I need to say that tan, the inverse tan of the number 6 divided by 20, that equals my angle theta. So when I put inverse tan of 6 over 20 into my calculator, I get that the angle is 16.7 degrees. Last question is a bit more challenging, question 4. This is a great example of how we can kind of do more extended problems involving more than one triangle and involving more than one skill. So this question is going to involve a little bit of Pythagoras as well as the sine, cos, tan stuff. So the first thing I'm going to do here to find this x is to work out what my missing side length is over here. I know that this whole thing is 18 meters, but I want to know what each one of these parts of that line is. So if this is my angle, then this is my opposite side, and this is my adjacent side. So I have that tan of 50 equals opposite, 12, over, and I'm going to call this y. 12 over y. I can now rearrange that the same way as I rearranged question 2 earlier to get that y must equal 12 divided by tan 50. And when I put that into my calculator, 12 divided by tan 50, I get 10.07. If this is 10.07 and this whole thing is 18, then this bit over here must equal 18 minus 10.07. So this bit here must be 7.93. Now I've got a right-angled triangle here where I've got 2 side lengths, and I'm looking for the third one, the hypotenuse. And for that, I'm going to use Pythagoras. So I know for Pythagoras that a squared plus b squared equals c squared. Therefore, x equals the square root of 7.93 squared plus 12 squared. And when I put that into my calculator, I get the square root of 7.93 squared plus 12 squared. It gives me 14.38 meters. And there we go.